Hey, so we're going to analyze the Aldol product, and what we're starting with is a known substance that I made, and so I know it's pure. We're going to analyze that NMR first, and then you'll be able to compare your experimental product to it. And we're also going to analyze the two starting materials, acetophenone and para-anisaldehyde, and you'll be able to compare those and see if either of those are present in your product when you do your experimental spectrum. Okay, here we go. Here's the spectrum. Notice that we've got everything integrated, and notice that if it says 1.89, it's a 2, and if it says 0.97, that's a 1. This is 3 to 2 to 1. This is our chloroform, and this is a 2 and to 3. And this water shows up in the chloroform solvent at 1.6, and then here's our TMS. Okay, everything else is product. Is our compound. All right, so the first thing you need to get that table that's in your assignment and fill in the predicted chemical shifts, and you'd use the table here. This is posted either here in this slide or it's in the last lab where we had it. I think Friedel Crafts, this is posted, or Diels-Alder somewhere. You can get access to this. Okay, so you're going to fill in the predictions, the predicted chemical shift, multiplicity, and integration. I'm not going to do that for you right now because I'm trying to keep this video short. You stop the video, fill those in, and then you'll do the actual chemical shifts from this known product and the coupling constants for D and E as we go. Okay, so here is our spectrum. Let's get the easy stuff first. All right, you remember that we've got this side here. These are the sp2 hybridized carbons with the hydrogens, and then this is the sp3 side. And so we can go, all right, we've got one sp3 carbon on here, so those hydrogens are going to show up over here on the right, and if you did your table, you'll see that they're somewhere around 3.8. Perfect. So this is H. Notice it's a methyl group, and it integrates to 3 hydrogens like you should have predicted. Okay, so now we're going to zoom in on this on the next slide so that you can see up close a little bit better. Okay, if you're reading along with the handout, I have some notes in there, and so I'm going along with that too. The first thing we're going to look for is our vinylic hydrogens. So it's the hydrogen E and the hydrogen D. And NMR spectroscopists would look at this and get kind of a thrill. I get a thrill when I look at this, okay? I'm noticing this doublet and this doublet because they're so wide, they're so obvious that they are equal in coupling constant, meaning the distance between here and here is the same. And so that tells you that, and that's a big coupling constant. For NMR spectroscopists, they notice that, okay? So, and also there's something neat about them. If you notice that the peaks aren't the same height, there's kind of a lean there, and there's kind of a lean here. That's a tell. That's a little secret message that they are coupled to each other, okay? So, all right, they're beautiful. So those are our vinylic hydrogens. And so we know that they're either D or E. So how do we know? And I'm going to show you how we can figure that out. It's with the resonance structures of the compound. Okay, so we've got, when you have a carbonyl, the electrons can end up on the oxygen. So let's draw that resonance structure.
How's that?
Hey, I'm recording right now. Okay, so what we've got is a positively charged carbon and a negatively charged oxygen. What's the next thing that could happen? These electrons can go here. So our oxygen is still negative, but this carbon down here is now positive. So the take-home message here is if you have a carbonyl with an alpha-beta alkene, I'm just going to do that, just show phi for those. This, let's see here, let me change colors again. This carbon and this carbon are partially positive. And so this is the alpha and this is the beta. So those two carbons that I did the green dots on, those are where nucleophiles would add. And they are also de-shielded. So this carbon and its hydrogens are going to be farther to the left. So that shows us that the beta carbon to the carbonyl is more de-shielded, it's more positively charged, and it's going to be farther to the left. So that tells us that E, out of these two, E is farther to the left and D is farther to the right. Okay, so there's a question on your NMR analysis to show the three resonance structures. Another thing we want to consider about E and D is their coupling constant. So the coupling constant between E and D would be JDE. And one thing that people look at when they're thinking about alkenes is that the coupling constant for cis alkenes is usually about 10 to 12 hertz. And if it's a trans alkene, it's usually about 15 to 19 hertz. So trans has a bigger coupling constant than cis. So how do we calculate the coupling constant? You looked at the handout, you'll know that we're going to subtract 7.814 minus 7.775, get 0.039. You multiply that times 400 megahertz, the size of our magnet, and you'll get the coupling constant. You can calculate it the same over here. Make sure this should be the same. And you calculate it, and you're supposed to make a comment about that in your calculated and make a comment in your questions. It would mean those three on the bottom. Okay, I just advanced the slide to the next thing. So we've got E and D assigned, and the next thing we're going to think about is some of the other hydrogens here. So if we think about this carbonyl, this is an electron withdrawing group, and this methoxy is an electron donating group. So that means that the hydrogen on the carbon closest to the electron withdrawing group, which would be A, is going to be more de-shielded because the electrons are being pulled towards, the electron density is pulled towards that electron withdrawing group. So we would go, okay, so farthest to the left then would be A over here. Now if we think about G, it's next to the electron donating group. So this would be more shielded and farther to the right. So this is G. Okay, so that leaves us with, we've got A, E, and D, and G all assigned. So F, B, and C are in here. And I just wanted to show you a few things that I can actually pick them out. I can pick out a couple of them. If we look at this doublet of doublets right here, it integrates to 2, and it's a doublet of doublets. Which one of these things did we say was going to be a doublet of doublets that integrates to 2? B. So that would be B. And then we've got a doublet here that integrates to 2, and that's probably this tall doublet here, which is F, leaving us with this little triplet down here, which is C. So C and F, though, are so close together, they're kind of on top of each other, that they're integrating to 3. We didn't split them up. So F, C, and B are pretty close in there, and I think it tells you in the handout that you can just kind of not come up with their chemical shift on the table. But you could go ahead and assign them if you can pick them out on your spectrum. Okay, and remember that this is the CHCl3. Okay, so that is the solved NMR of our product. One other thing I wanted to show you is, again, the lean here. Notice that A is leaning this way. And if you look at B, it's got this peak, and this peak. That triplet or doublet of doublets is leaning that way, showing that B is coupled to A. That helps us see that B and A are probably the two things coupled to each other. And then on F here, F is leaning that way, and G, so it's leaning towards G. Okay, and remember we've got D and E leaning towards each other. It's just a little something that is a finer thing on the NMR that you can look for, that lean. Okay. All right, so here we've got the p-anisaldehyd. So let's draw the structure, make a table. We've got an aldehyde and an O-methyl here. And that's what p-anisaldehyd looks like. So we're going to go, let's see. Here it is. A, B, C, and D. So we'll quickly make a table. Y'all, I will expect you to have this table. So parts per million for A, that's going to be around 3.8. I think that's what it, yeah. And B and C are 7.3, again, just for the for benzene hydrogen. And then D is a 9.7 for the aldehyde hydrogen. Okay, so we can do the integrations. A would be 3, B would be 2, C would be 2, and D is 1. And then for multiplicity, S is a singlet, B would be a doublet, C would be a doublet, and D would be a singlet. So looking at this, we can see we've got the thing at 3.8, so that would be A, D, and then B and C. We have to again consider electron donating and electron withdrawing groups. If this is an electron withdrawing group and this is an electron donating group, B would be more shielded because it's close to the electron donating group. So more shielded is farther to the right, and C would be less shielded, so it would be to the left. Okay, so that's the analysis of that. You can look, if you see an extra methoxy and these peaks present on your spectrum, then maybe you've got the this as an extra, impurity. So here is the acetophenone starting material. Let's draw the structure. It's a ketone. So that's acetophenone. We can go A, B, C, and D. And you can make your table. So A would be, it's a methyl next to a carbonyl, and I think that on the table is somewhere around 2 to 2.3. This is ppm. B would be 7.3. All of these we would just say are 7.3, just to kind of get in that area. All right, A would be a singlet, worth 3 hydrogens. B would be, it's coupled to C, so it's a doublet, worth 2 hydrogens. C would be a doublet of doublets, worth 2 hydrogens. And D is a triplet, worth 1 hydrogen. So if you look at the spectrum, we can see easily A. And then let's think about the electron withdrawing group. The carbonyl, B, is going to be the most deshielded, so B would be down here. And then C and D are in a clump here. We can't really tell them apart. So that is your analysis of the acetophenone. Okay, so now you're supposed to process your own experimental NMR by adding the chemical shifts and integrating each peak, compare it to the known NMR and the two starting materials to determine if it's pure or if there are impurities. So your assignment is to have all of these things: your analyzed pure aldol product, your analyzed acetophenone, your analyzed p-N-acetyldehyde, and your analyzed experimental NMR spectrum with the structure and the labels, and answer all the post-lab questions and the NMR questions. This is due Friday at 6 p.m.